This is part 3 of the video notes for Objective 10 vectors. These notes correspond to sections 5.4 and 5.5 in your textbook. In the last video, we talked about operations with vectors objectively, abstractly. So no context, no meaning, no word problems, just do the operations. And in this section, we want to see how these operations relate to the applications. So the first thing we want to talk about is when you add two vectors together. So in the last video, we talked about the sum of vector A and vector B being the sum of their components. But what does this look like, and how does this relate to forces, like adding forces or adding velocities that are opposing, wind versus an airplane, weight versus a ramp, that kind of thing. So we're looking at two vectors acting on a single point. And we have one vector going in one direction, and we have another going in another direction. Well, if we wanted to find the net force acting on the object, or the resulting or resultant force, we would add the two vectors together. So to draw this out, the trick to finding a resultant force is to take the initial point of one vector and put it on the terminating point of the other. So we're going to go ahead and do that with vector B, and I'm going to do my best to draw these so that they have the exact same direction and magnitude. And you can see by doing this, what we've created is a parallelogram. Oh yeah, not a perfect parallelogram. So the resultant force is the vector from the initial point of A to the terminating point of the new vector B. Using the parallelogram law, we can draw our 200-pound force here, connect the parallelogram, and we know that the resultant force is this vector right here. So what we want to do is find the resultant force, its magnitude and its direction, if we have 100 pounds and 200 pounds acting with 30 degrees in between. Now again, I recommend you align one force with the x-axis, because now we have a vector with a magnitude of 100 and an angle of 0 degrees. And we have another vector with a magnitude of 200. And since this is at 0, the angle in between the two vectors is just our 30 degrees. So how do you find a resultant vector? Well, you need to add the vectors together, and adding the vectors together means adding their components. So we need to know the x and y components of each vector so that we can add them together. Think v1x plus v2x, comma, v1y plus v2y. Well, this is where trig plays a part. We know that the x component of a vector is r cosine theta, and that the y component of a vector is r sine theta. And since we know r and theta, we should just be able to plug these in to our sum. So the resultant vector has a component form of 100 cosine 0 plus 200 cosine 30, comma, 100 cosine 0, I said 0 and wrote a theta, plus 200 sine 30. So let's calculate this. I know cosine 0 is 1 and sine 0 is 0, so this eliminates, and this becomes 100 plus, well, cosine of 30 degrees is rad 3 over 2. 200 times rad 3 over 2 is 100 rad 3. And over here, this eliminates. Sine of 30 degrees is 1/2. 1/2 of 200 is 100. So now I have exactly the component form of my resultant vector. This still doesn't tell me its magnitude or direction, but gives me the information that I need in order to find the magnitude and the direction. So now you can imagine that this is x and this is y, or you can think of it as your adjacent and your opposite side. we're going to find the magnitude using our magnitude formula. So the magnitude will be the square root of 100 plus 100 rad 3 squared plus 100 squared. And I've done my job of keeping it exact. At this point, I can type it just like this into my calculator and give myself a rounded answer. So I get that the resultant force is about 290.9 or 291 pounds. The next thing I need to find is the angle, and since I know the opposite and the adjacent side, I can just take the inverse tangent. Theta is equal to the inverse tangent of 100 over 100 plus 100 rad 3. Now, I could simplify this by a factor of 100. I could rationalize my denominator, but I don't need to do either of those things. I'm just going to type this into my calculator as the inverse tangent of all of that, and I find that the angle of the resultant force is about 20 degrees. So we find that if you have 100 pounds of force acting in one direction and 200 pounds of force acting 30 degrees away from that, you get a resultant force of 291 pounds that acts 20 degrees from the origin, from the positive x-axis. Let's try a more contextual example. The key to solving application problems is being able to model the problem. So we want to find the amount of force needed to push an 800-pound block up a 10-degree incline or a 10-degree ramp. In your picture, you drew a horizontal with a ramp and labeled the angle of the ramp 10 degrees. You also need to draw your block, which is 800 pounds. And there's a few forces acting in this problem if you're trying to draw a force diagram. So, for example, the block's weight is an 800-pound force directly down. And its component form would be 0, negative 800 if this point were to be considered 0, 0. Then the force we're looking to solve for is the force along the ramp, since we're trying to push this block up the ramp. And we can use the parallelogram law because the resultant force is a force that makes a 90-degree angle with the ramp, and the rest of the parallelogram looks like this. Well, looks like this if I'm drawing a more accurate picture. Degrees, and what we know about triangles and 90-degree angles to find all of our labeled information. For example, I know that this side is my 800 pounds. And I know that this angle must be 80 degrees since this is a right triangle. Well, this angle must be 10 degrees, supplementary angles. And since this is a right angle, this is also a right angle. And this must be 80 degrees over here. So how does this help me solve? Well, the vector I want along the ramp is congruent to this side of the parallelogram. And this is helpful because I have an angle, I know its hypotenuse, and I want to know its opposite side, which is the perfect setup for sine. Sine of 10 degrees is equal to x over my 800-pound force, or x is equal to 800 sine of 10 degrees. Using your calculator in degrees, you get that your resultant force is about 139 pounds. So you would need 139 pounds of force to push this block up the ramp. Every other application problem is a variation of this setup. Now in this one, I was looking for the resultant force, but I could give you the resultant force and the weight and ask you to find the angle, or I could give you the resultant force and the angle and ask you to find the weight. These would all require the setup of sine is opposite over hypotenuse, similar diagram. The only difference maybe would be if you're finding the angle, you'll need your inverse sine. So let's try a slightly different application using navigation. So from a navigation question, you can find a few things, and we're going to find them all. So we're going to find the drift angle, the ground speed, and the course of the airplane. And if you translate this question into the vocabulary of vectors that we've seen previously, we're basically finding the direction, the magnitude, and the component. Now this problem did the work for us of wanting to align one of our forces along the positive x-axis because it gave us an airplane heading due east, and due east is the positive x-axis. So how can we draw a picture of this airplane's path? Well, let's start with a vector originating, and we'll call this 0, 0. So we're going to go towards the east, and we're going to label it with its magnitude, which is 200. Then we have a wind out of the south. Now, notice they say the bearing is 0 degrees. This is not 0 degrees on our standard plane. This is a bearing of 0 degrees, which actually begins at the north and rotates clockwise. So a bearing of 0 degrees means straight up. And so the wind is acting at 40 miles per hour. And the question is, what way does the plane go? So you can imagine if you set this up by placing your wind vector at the end point of your airplane's vector and create your parallelogram, which in this case, because of the 90-degree angle, is actually a rectangle. You know that you're trying to find this diagonal. So let's write the airplane and the wind in their component form. Because the airplane is heading due east, its component form is 200, 0. Since the wind is heading due north, out of the south means to the north, its component form is 0, 40. We're going to add these two together. And it's pretty basic in this example because of the 90-degree angle in between. We don't have to break it down to its x and y components since they are perpendicular to each other. The resultant force is 200, 40. That means that the angle, which is opposite over adjacent or tangent, is going to be the inverse tangent of 40 over 200. Again, because I'm using my calculator, I don't have to simplify this fraction. I can just use it the way it is. And I get that the angle, or the drift angle, is approximately 11.3 degrees. Now, in a real-life context, I'm going to be slightly more accurate and carry more decimals because in real life, you actually need a high level of accuracy. Even a tenth of a degree off would cause a huge difference in a plane's path as it travels hundreds of miles to its destination. The next thing I want is the ground speed, which is aka the magnitude. So I'm going to find the square root of 200 squared plus 40 squared. I don't need to simplify this. I can just use my calculator. And we get that the plane's course will be with a speed of approximately 204.0 miles per hour. The last thing we need to find is the course of the airplane, which is the components x and y, or in this case, west and north, that the plane actually ends up navigating. So we're going to write the component form as the magnitude cosine the angle and the magnitude sine of the angle, since we know that the x coordinate or the x component relates to cosine. and the y component relates to sine. Simplify these with a calculator, and you get that the plane's heading is slightly nudged as far as the horizontal component goes. Includes the video notes for the applications of vectors. There are plenty of variety in the problems you've been asked to do in the textbook, so don't hesitate to ask questions as to how to draw the picture, how to find the missing angles, or how to solve for the different forces.